Okay, when I see something like this, it's very easy to get overwhelmed, right? Um, but there's a couple things in my head that I'm doing right off the top. It doesn't matter which circuit I'm looking at, right? First thing is I'm evaluating all the information that they've given me, okay? Because that's going to dictate where you can start, right? If they give you two spots, like if they give you two pieces of information somewhere, then just use those two pieces of information to calculate the third, right? That would be my logical starting point. The problem with this question is when I look at all this stuff, it told me the voltage at the battery, which tells you the voltage and like the voltage that has to be lost in the entire circuit, right? So you have that going for you, and um, but they also told you every resistance, okay, and nothing else. And so if they've only told you the resistance, that in my head tells me, okay, I'm gonna have to calculate what the overall resistance looks like for this entire circuit, right? Which we call the equivalent resistance. Okay, if you guys remember. And the second thing is, now that you've decided, okay, well, I've looked at the information that they've given me, I've kind of come up with a first step based on what's there, because you can only do what you can do. And based on what they've given me, it seems like the only thing I can work with is the resistance at the moment, right? Nothing else. And so the second thing that I'm thinking about is whether or not, or which set of Kirchhoff's laws am I going to apply here, right? Remember, Kirchhoff was the guy who like came up with these laws for whether or like how a circuit was wired, right? Whether it's in series or parallel. Okay, when I look at this, remember in a series circuit, the electrons only have one choice of travel. They start at the battery and they go around one choice and they come back, right? That's a series circuit. That does not appear to be what is in this question. Okay, it looks like, and this is the start of the question, I suppose. It looks like the electrons can follow this like, or one second, I'm going to use the same colors just to keep it consistent with my solution here. It looks like the electrons can take the blue path, right? And then it looks like, oh, well, they could probably also take the green path. But then they could also take the other path. There's one more here, right? We could take this yellow path, right? And because the electrons have choice of travel, let's say choice of travel, that means it's in parallel. Okay, and those are the laws that you're going to apply, okay, across the circuit. Okay, from Kirchhoff's laws. Does anybody have any questions so far? I see three possible routes there. Okay, now, what I would say now is we're going to, I would say the first step here, got a letter sitting there. Let's say I'm going to find, we've already identified the fact that I can only work with the resistance, right? So I'm going to find the equivalent resistance. Okay, that's step one. And it's for like a parallel circuit, right? So you guys remember it's 1 over RP, right? And we're going to add up all the fractional values, right? So the catch here is, though, the thing what makes this so difficult, and this is what kind of stumped me when Elizabeth asked me about it in the first place, we have to think about where are the choices that are like the, let's say, on ramps for traffic that have a choice of where to go, right? Let's identify those. Well, one of the choices that the electrons have is right here at this junction. Maybe I'll use a red or something so we can see, right? Right? The electrons can either go this way or they can go this way, right? And it also looks like they can have a choice here as well, right? They can go that way or this way. And that's what makes having a choice is what makes this particular circuit being in parallel. It's choice. Okay, and so what I would say is to start at the furthest point and work backwards, right? So I'm going to start basically at I5 here, or R5, the junction here, and I'm going to figure out the resistance parallel going on in there. Okay, so I'm find RP for this choice. Is everybody okay so far? This is kind of the process that I had to step myself through in order to explain all the answers that ultimately are on your solutions, right? So what I'm going to do here is just spell this all out for you. Okay? So I'm just putting into words the process that I think you guys should follow when you look at a question that is this complicated. Okay, so I'm looking at the furthest choice, right? And I'm going to work backwards back to the battery. Okay, so I'm going to find RP, right? Or find the equivalent resistance for that first junction, right? Which I think I'm just going to denote as, I'm going to denote this one here, RP1. Okay, I'm just going to find what the equivalent resistance for this portion of the circuit is. Okay, so let's just do that. Well, here, I'm going to write some notes. That way they're on here when I post them. Okay, so the furthest junction is going to be R4 and R3. Okay, so I'm going to find what we're going to call RP1, right? There. Okay, so that's going to take 1 over RP1 has to equal, you're going to add up the fractions, right? Because this is what we're doing. It's in parallel, so I have to find it's a proportion of the resistance, right? Because the electrons aren't going to experience 18 and 36 every time they go around. They're going to experience on like almost like an average, right? Because they're going to go one way one time and then another way the second time, right? So we got to find like kind of almost like an average amount of resistance that they're going to experience every time they go through there, right? That's what this is. So we're just going to add these two things together. Well, okay, that has to equal 1, oops, I'm on eraser, 1 over 18 plus 1 over 36. And how do I add these two things together? Got to create a common denominator. Well, that's 2 over 36 plus 1 over 36. It's going to be 3 over 36 has to equal 1 over RP, 1. And then we learned yesterday, cross multiply to solve for what RP1 is. That's what you're after, right? And we're going to see 3RP1 has to equal 36. So RP, what happened there? RP1 is equal to 36 by 3, which is equal to 12 ohms of resistance. Okay, so that's what the electrons are going to experience on this portion of the circuit. Does anybody have any questions? Now something else happens, right? Something else happens here. If the electrons, I'm just backtracking here. I'm just going to have a look. I'm just going to backtrack right to here. Let's say that the electrons choose to go this way in the first place. They have no choice but to encounter this other resistor that's sitting here, right? They have no choice. All of them are going to experience this 4 ohms of resistance. In addition to, after they get through there, they're going to then experience all 12 of this. Okay? And so we need to incorporate that into, if the electrons choose this green-yellow path, they're going to experience that 4 ohms of resistance no matter what. Okay, so I have to take point 2 here, or step 2, is electrons that take this path four ohm resistor. I think it's called, what do we call it? R5. Like, they have no choice, right? And so we're going to add this to the 12 ohms we just found for the green-yellow portion, right? And so we're building this total resistance almost, right? RP total is going to be 12 ohms plus 4 ohms, which is going to be 16 ohms for RPT so far. Okay, any problems? Okay, now, as I said, we're looking for this like RP total, right? The total amount of resistance that these things are going, the electrons or vehicles are going to experience in this entire circuit, right? But part of what we just did there was incorporating this 4 ohms of resistance, right? But then, oops, I think we're okay. But then we also have to take into consideration now, right? I now have just found all the resistance over here on this portion of the circuit, right? Found everything in that purple box. I've taken into consideration all the resistance there, right? Now, we have we have a choice here, right? So I have to take into for RP1, how can the electrons experience less resistance? Jagger, it's like an average number, right? So like on any particular travel or loop around this circuit, they can choose as to whether or not to go around the yellow circuit or the green one. So what RP does is it finds like it can't keep track of what they do every single time. So it's almost like an average, right? It's like, okay, for this portion of the circuit, the electrons are going to experience on average was 16 ohms we said? 16 ohms. 12 ohms. Oh, sorry, no, sorry, the 16, I was right. Okay, because they encounter this no matter what. No, it's like an average, Jagger. It's not an average. It's like an equivalent resistance. Something different. You'll see, Jagger, that it's just kind of trying to simplify the parallel circuit so that at the end of the day, every loop that these electrons do, they come back to the battery losing all 20 volts. Okay, that's the most important thing. Kirchhoff's law, like any law, right? It doesn't matter if it's series or parallel. As soon as you hook up a circuit and electrons are flowing, they have to return back to the battery having lost energy. If they don't, that's where you start seeing like they're trying to lose energy, and that's where things heat up and ultimately catch fire, right? That's why we have things like resistors or loads, right? Is the electrons have to give off some of that energy, right? And so the most important thing is that they arrive back for what we'll call a stable circuit. They have to arrive back at the battery having lost all 20 of the volts that they initially started with, potential energy. Okay, and so all this, like, what this equivalent resistance is doing is calculating. It's like giving you like it's not an average, but it's almost like an average, right? It's keeping track of, because it's not going to tell you there's no way for it to keep track of whether or not it went this way or it went this way. So the best we can do, Jagger, is figure out, okay, what as we hook this thing up, what is it going to experience, knowing that I can't find which path it's going to take. So I have to take it all into consideration, and that's what equivalent resistance is if they take this path, right, they're going to experience 12 ohms of resistance. 16 ohms, 16 ohms. Okay, this number here. Because the electrons are flowing like crazy fast, right? Like, it's not as if they're just going to do one lap and then that's it. Like, in 1 second, they're probably going to go like, I don't even know, tons. So it's not as simple as just saying, oh, it's going to be like 18 ohms or something like that, right? It's as soon as you hook that thing up, it's gonna rip through there, right? Is that okay, Jagger? That's about as best of an explanation as I can give right now. Okay. Just like the most important thing, Jagger, is that they return back with no potential energy. Okay. So let me run through. Maybe by the end, Jagger, it'll make sense. The numbers all make sense sometimes, I think, right? So you guys know, it's, again, this point right here is a decision point, right? And so we have to do our equivalent resistance for parallel circuits again. But this time, the electrons full well know, okay, well, if I take the route in the purple box, I'm going to experience 16 ohms of resistance. If I take the blue route, I'm also going to experience 16 ohms of resistance. Okay, so again, what we're trying to do is calculate an equivalent resistance for the blue box, right? Because the electrons are making a decision here as well. The blue box is all about the decision at the first junction, and the purple box is all about the decision that the electrons are making at the second junction. Okay? And so what we're trying to do is create, ultimately, this black box here, or the circuit itself, is RT, the total amount of resistance that the electrons are going to experience. The problem is we have a few other subset of boxes inside of our parallel circuit that we're trying to find, right? But in order to figure out what RT is, I have to figure out what the equivalent resistance in the blue box is, and I have to figure out what the equivalent resistance in the purple box is. Okay, so I guess now that's a little bit different than the way I kind of like written it earlier. For this one, I'm trying to find for the blue box, right? And so the same thing applies here. We know in the purple section, it's going to experience 16 ohms of resistance, and we know in the blue section, on the blue path here, the only resistor that it's going to experience on the blue path, aside from the very one at the end, is going to be the 16 ohms, right? So I'm going to find the equivalent resistance for the blue box is going to be 1 over, let's say we'll call it RPB, blue. It's probably a better way to do it. I was having a hard time figuring out how to label this morning, clearly. So we're going to have the 1 over 16 from the purple box, and I'm going to add the 1 over 16 from the blue box, right? That's from up here. Okay, and so we're going to get 1 over RPB is going to equal 2 over 16. If I were to solve for RPB, Okay. Okay, so no matter what, I'm going to go back up. I'm going to read this and then I'm going to go back up. No matter what, we learned that the electrons just can't magically vanish off the circuit. They all have to combine after they've made their choice and head back to the battery. Okay, but there is one more thing on the way back to the battery. That's RP1, right? RP1, sorry, R1, not RP1. R1 is 2 ohms. They all the current, doesn't matter if they chose the blue path or the green or the yellow, they're all going to be right here, right? And no matter what, on their way back to the battery, they're going to experience this 2 ohms of resistance, right? So we have to take the blue box, RPB, all the equivalent resistance that we found from being in parallel in the blue box, right? That's all fine and dandy. But we also have to add in the fact that they're all going to encounter this resistor, all of them. Okay? And so I have to go RPB plus R1, okay, which is going to be 8 plus 2, which is equal to 10 ohms. This, everyone, is what we call RT. This is the equivalent resistance for the entire circuit. Okay? So this entire circuit, as the electrons go around this whole thing, they're going to experience 10 ohms of resistance. So that is a piece of information that you can come up here to your VT. Underneath your VT, you can write, okay, they're going to experience 10 ohms of resistance. Okay, this, everybody, is the hardest part of this entire question. Now, it's just, there's a little bit of a puzzle back solving, right? But you now know VT and RT, you can find the total amount of current that exists in the circuit, right? You're just now going to follow the information where it leads you, okay? So every time you find 2 things, you can find the third. So that's what we're going to do now. So step 1 was all about finding the equivalent resistance, which is a very large task for questions like this, right? Am I going to ask you one this complicated? No, okay? But if I provide you, it doesn't matter what the circuit looks like, if it's in parallel and I give you all the resistances, that's going to be your starting point, right? Because that's all you can deal with. And then once you find the equivalent resistance, now you know 2 things. So you can find the third. That's what we're going to do right now, right? Find IT, total current, or the total number of cars. Okay? So to do that, we're going to say VT is equal to IT times RT. Plug in the numbers. Well, total voltage was 20 volts, divided by the resistance total, which we just found to be 10 ohms. That's going to tell you what the flow, what the current is, right? How many electrons are flowing, right? So we're going to find that it's 2 amps of current that we're going to measure. Okay, so now I go back up here and I say, okay, great, I found this, 2 amps. So we know along here, when they arrive at the blue decision point, there are 2 amps of current that have to make a decision. Okay? And then we know, just write down here. This gets this is a lot of writing, but it's the exact thought process that I had as I worked through this hard problem. And it's at least if you guys have this, you can refer back to this. And it's the sort of thinking that you guys are going to do as you work through questions like this. It can be harder or easier, but it's the thought process, right? There's quite a bit, and it's quite extensive, but they're all little calculations. It's just about the series in which you're doing things, right? So no matter what, right, there has to be 2 amps at I1. All current must recombine before going back to the battery. All right, which means we can find, well, let's go up. That must mean that I1 here, if all the current has to combine back to go back to the battery, that must mean that I1 is 2 amps, right? Because current just can't magically disappear. It's all got to come back to the battery. Okay? So, now you know 3 things here. Or 2 things. We can find the third. Right? We can find V1. Right? V1 is going to equal I1 R1. Two amps times a resistor of 2 should equal 4 volts. Okay, does anybody have any problems with that? Okay, from here, and this is some of this is me putting Kirchhoff's laws into real words, right? We know that the electrons must lose all 20 volts of potential they start with, right? So we know that they're all going to lose 4 volts at the very end. At, we'll call it R1, right? We know that to be true, which must mean they lose, and I'll write this down, then we'll go up and look at it, 16 volts at V2. So V2 is equal to 16 volts. How is that true? Well, let's go look. V2 is right here. Right? We must, like, if the electrons choose this blue, and I know it's starting to get a little convoluted and we can't see it, this blue path, right? We know that the electrons must lose all 20 of their volts of potential energy, but we're going to lose 4 at V1. Well, the only other resistor that they're going to encounter on that blue route is R2, right? And so if they lose 4 here and they need to lose 20, well, the difference here is going to be 16. And now you know 2 things here. You can find the amount of current that decided to come in this direction, right? So we can go find I2. Oh, 16, sorry. Looked like a 10 in my head. Nope. Okay, so we know that 1 amp of current decided to take this route, which must mean 1 amp took the green and yellow, right? But we just don't know how that's split up yet. So that's our next step, right? Well, we do know that at I5 then, if 1 amp decided to come on this route, then 1 amp would be here at I5, right? Just bear with me, guys. I'm just going to write down everything. If you guys are good, I don't know. Sorry. I just want to write everything, make sure everybody's all good. 2 amps, because this is not easy. It's like a big puzzle, right? Okay, now you guys can find, oh, I'm scrolling on my computer, but you guys can't see it because you know 2 things at I5 now. You know the resistance and the current. You can find the voltage here at I5, right? So let's do that. Well, it's just the same equation all the time, right? Four ohms. You get, oh, not 4 ohms. It's 4 volts. You can fill that in. Okay. Now the trick here is, the last little tricky bit is like how much current, you know, how much current went along the green path and how much current went along the yellow path. That's kind of the last hard part of this question that we got to answer, right? So that involves, like, we're at that decision point. We need to decide, well, we're back into our voltage kind of discussion, right? So the only other resistor here, right? We're thinking about the electrons and how much energy they have to lose. That's voltage, right? So we know, let's just here for a second think, I'm just going to pull out the green highlighter. I'm going to go on this green path. Maybe I'll actually do it in pencil, green. I'm going to go along this green path. You can't even see it. Which resistors did I come in contact with? Well, 4 volts here, or the 4 ohm here, and then the 36 ohm resistor here, and then the 2 ohm resistor there, okay? What were the voltages at each of those points? Well, I'm going to lose 4 volts of potential energy at 5, and I'm going to lose 4 volts of potential energy at R1. But I know I have to lose all 20 volts that I started with, right? Well, that must mean that if I lose 4 volts at V1 and 4 volts at V5, V3 must be 12 volts, right? Because 12 plus 4 is the 20 that I'm looking to get rid of. Okay, I'll put that into words. Any questions? Almost there, guys. 3 more steps. Okay, now that you know the voltage there, you can unlock this piece of information, right? Which is ultimately one of like the last things that we need to figure out. How much current decided to go on the green path and how much current went on the yellow path. That's what we're after, right? But you now know, two of the pieces of information along the green path. So you can find the third. So we're going to find I3. Okay? We're going to find I3. And I3 is going to be V3 divided by R3. Right? How did I get that? That's just V3 equals I3 R3, right? And I just rearranged just in case anybody's freaking out. Okay? So we can find, if after I plug in the numbers, I'm going to plug in the fact that V3 was 12 and R3 was 36. And so we get 1/3 of an amp going this direction. Okay? And then you know for sure, well, 1 amp is going around this portion of over here somewhere, right? Between the green and the yellow, we know there's 1 amp. Well, 1/3 of it decided to go on the green path, which must mean that I4 over here has to be 2/3 in order to equal the 1 amp. Okay? Okay? And the last step, and ultimately the very last thing that you need to figure out, is once you know that that is 2/3 of an amp, you can find what V4 is, and every piece of information on this circuit, despite it being very complicated, has been filled in. Okay? So we go down and we say, okay, no problem. Step 11 here is find V4, right, to be equal to I4 R4, and we're going to go 2/3 times 18, which will equal 12 volts, and everything has now been filled in.